All right, let's talk about nuclear power. We're going to go deep inside one of the most powerful and, let's be honest, misunderstood technologies on the planet, the nuclear reactor. We're going to pull back the curtain and show you how it all works, starting with the tiniest atom and building all the way up to those massive plants that power our world. Okay, let's get into it. And that might sound a little dramatic, but honestly, it's the absolute truth. The entire incredible art of nuclear engineering, the thing that separates clean, steady energy from an unthinkable weapon, is all about mastering this one little number. So what is this K thing and how in the world do you control it? That's really the core question we're going to answer today. So here's our game plan. First, we'll look at the mind-blowing energy locked inside a single atom. Then we'll dive into how engineers control that power in a chain reaction. After that, we'll see how they turn all that heat into electricity. And of course, how they build in layer after layer of safety. We'll also tackle the big one, the spent fuel challenge. And finally, we'll look at what's next for nuclear power. All right, first up, energy inside the atom. To really get nuclear power, you've got to start small, like impossibly small. We're going inside the nucleus of an atom, where this immense force, they call it binding energy, is literally holding the universe together. So, how do we get that energy out? Well, it's a process called nuclear fission. Basically, you take a big, heavy atom, like uranium-235, and you split it open with a neutron. But here's the wild part. Look at that number. Fission releases over 50 million times more energy than a chemical reaction, like burning coal. No, that's not a typo. 50 million times. It's just staggering. Now, to really wrap your head around a number that big, let's look at this. It's a single uranium fuel pellet. It's just a little ceramic cylinder, about the size of a gummy bear. And get this, that one tiny little pellet has the same amount of energy as a ton of coal. An entire ton. This right here, this incredible energy density, is the whole reason we even bother with nuclear power. It's why you don't see mile-long trains delivering fuel to a nuclear plant every single day. Okay, so part 2. Controlling the chain reaction. We've got this almost limitless power source, but, releasing it all at once, that's a bomb. The real genius here is controlling that release with absolute pinpoint precision. It's like a quantum tightrope walk, and it's happening on a massive scale. So let's get back to that number from the beginning, K. It's the neutron multiplication factor, and it's all about balance. In a reactor, engineers are in a constant fight to keep K pinned at exactly 1.000. One fission leads to exactly one more fission. The reaction is stable, sustained, and totally under control. We call that criticality. Now, in a bomb, you let K go way above 1, and the reaction explodes exponentially. So the million-dollar question is, how do you keep it perfectly balanced at 1? The secret, the thing that makes it all possible, is this tiny number, 0.65%. This little fraction is, and this is no exaggeration, probably the single most important safety feature in nuclear physics. And here's the coolest part. This isn't some clever engineering trick. It's a gift from physics. You see, most neutrons from fission pop out instantly. They're called prompt neutrons. But this tiny 0.65%, they're delayed. They kind of hang back for a few seconds. And that little delay, that's everything. It stretches the reaction time from microseconds to a timescale that we, humans and our slow mechanical systems, can actually manage. Without those delayed neutrons, a stable reactor just wouldn't be possible. All right, on to part 3, the nuclear steam kettle. So we've managed to master quantum physics to create a perfectly stable, incredibly hot fire that never goes out. And what do we do with all this incredible cosmic power? We boil water. Seriously. At the end of the day, a nuclear power plant is just the world's most sophisticated and powerful steam kettle. Now, in the US, there are 2 main flavors of these steam kettles. First, you've got the pressurized water reactor, the PWR. That's about 2/3 of the fleet. It uses crazy high pressure to keep water super hot but still liquid, and then it uses that heat to boil water in a totally separate loop. The other one is the boiling water reactor, or BWR. It's more direct. It's like, hey, let's just boil the water right there in the reactor and then send that steam straight over to the turbine. Just 2 different ways to get the same job done. Okay, let's talk safety, because this is probably the most critical part of the whole story. The entire safety philosophy for nuclear plants is called defense in depth. And the idea is actually pretty simple. Don't ever rely on just one thing to work. You build multiple, independent, redundant barriers. You build a fortress so that even if a few things fail, the public is still totally safe. Let's just walk through these layers. It's like a set of Russian nesting dolls. Barrier 1, the fuel itself is a solid ceramic, and it traps most of the nasty stuff right inside it. Barrier 2, you seal those pellets in a special metal tube. Barrier 3, all those tubes are inside a massive steel tank that's almost a foot thick. Barrier 4, the whole shebang is wrapped in that iconic concrete dome you see from the highway, and that thing is over a meter thick and laced with steel. And finally, there's a big planned buffer zone around the entire site. It's just layer upon layer of safety. All right, now for the big one. The question everyone always asks, what about the nuclear waste? What do you do with the fuel after it's done? This has been the unresolved chapter of the nuclear story for a long time, and it's a huge public concern. So let's actually break down what it is. So when you hear spent fuel, you probably think it's all just hypertoxic radioactive gunk, right? Well, check this out. Over 95% of it is just unused uranium. It's not waste at all, really. It could actually be recycled and used as fuel in new advanced reactors. The really nasty, highly radioactive stuff, the fission products, make up less than 4% of the total volume. And that radioactive stuff doesn't stay that dangerous forever. Its radioactivity decays over time. For the first few hundred years, yeah, it's very hot and very radioactive. But after about 300 years, the most intense stuff has decayed away. And here's the real kicker. After about 10,000 years, the leftover material is actually less radioactive than the natural uranium ore we dug out of the ground in the first place. That's the scientific logic behind these long-term storage plans. So all of this brings us to the future. With this huge global push for clean energy, where does nuclear power fit in? What's its value proposition in a world that's trying to get off of fossil fuels? Well, here's the case for nuclear, plain and simple. First, it's what's called firm power. It's on 24/7, rain or shine, windy or not. Second, its land footprint is tiny. We're talking 100 times less space than wind or solar for the same amount of energy. Third, it's clean. It produces basically zero carbon emissions. And finally, the technology is getting even better, with new designs like small modular reactors that promise to be even safer and cheaper to build. You know, the source material we reviewed for this really nails the conclusion. The physics is solved. The engineering is proven. The safety is incredible. So the final question isn't really for the scientists or the engineers anymore. It's a question for all of us, for policymakers and for citizens. The reactor is ready and waiting. The real question is whether we'll choose to turn it on.